Hi, everyone. Welcome to another session of the Data Learning Seminars, the last one of the year. And today we have Kay Hodesdon from Stability AI. She's a senior machine learning engineer. Where she works in inference. Kay brings to Stability AI her expertise in optimizing deep learning performance, acquired over 4 years working as an ML engineer at an AI chip startup, GraphCore. Kate studied mathematics and philosophy at Oxford, where she became fascinated by the foundation of mathematics. Kay went on to do a PhD in philosophical logic, followed by research as a postdoc at the University of Lorraine, France, and a visiting fellow at Harvard University, before moving into the field of machine learning. Her diverse background gives her a unique perspective in the implications of artificial intelligence, as well as technical expertise in the workings of underlying models. Thank you, Kay, for joining us today, and I'll leave the audience with you.
Thank you so much, and thank you for the invitation. Okay, so I want to talk to you about the state-of-the-art deep learning architectures for image generation, which is latent diffusion models, and some of the recent improvements to them. So I work at Stability AI, and we have one of the industry's largest inference as a service platforms doing generative AI. So our flagship model is image generation, although we also do video, 3D renders, audio, and other kinds of generative modeling. So what do these models enable? One of the main promises of generative AI is that you can create media on the fly. So this allows you to be extremely responsive, creating something completely novel in real time. And this brings interesting performance challenges, which is what I work on at Stability, where I focus on inference as opposed to training. So you can trivially personalize images to really fine-grained demographics, which is what I've referred to here as hyper-personalization. Or you can hand that ability to generate things over to your end user, so they can customize what they're seeing and things like video games, for example. So this ability for really open-ended generation allows you to avoid a lot of laborious work, such as post-production work in film, where you may need to, say, cut something out of a shot or extend a shot. You can now do this programmatically with models rather than needing to do this manually. So here are some use cases, and then everything I've said goes analogously for video, 3D, audio, and other media. Okay, so what's the problem that we need to solve? We want to be able to sample from an unknown, very complex distribution, and this is the distribution underlying the kind of images that we want to generate. Okay, so let's think about this. Call that distribution P of X. We don't know P of X. It's extremely complex. And P of X isn't just the training data. P of X is the space of all image-like things. Okay, so it's continuous, and there will be areas of high probability and areas of low probability. So this image is supposed to be a kind of heuristic. Think about the space of all cat images. There are areas where the probability density is high, and samples are therefore likely. And then there are low areas where you would not expect to find any samples. So data taken from those low areas would be non-structured. Okay, it would be noise, not cats. So sampling from the space means generating a synthetic data point that has the same relevant structural properties as the class members. So it will be something that looks cat-like. So it's maybe unnatural, depending on your background, to think about images as being data points in a big space. But you can motivate the idea if you first of all think about a more restricted space and then extrapolate up. So first off, just consider a 2-pixel grayscale image. Each pixel has a color, which is somewhere between white and black. If you say that 0 represents white and 1 represents black, then you can represent any 2 pixel shape like this as 2 coordinates in 2-dimensional space. So for example, this object over here would be represented by this point in 2-dimensional space. So here is pixel 1's color, and here is pixel 2's color value. It's something like this. And then if you were to slide this point around, the color intensities of your 2-pixel object would smoothly vary. For a 4-pixel object, it's the same deal, except now you would need 4 coordinates. Okay, so you can see that an n-dimensional vector would represent any n-pixel grayscale object, including those privileged n-pixel grayscale objects that are images. And what we care about is images, which, unlike noise, right, this kind of thing, images are structured. So images are kind of like these special rare combinations in the broader space of noise. So here we have an MNIST digit in 28 by 28 grayscale pixels. And if you think about this kind of digit in general, like digits 0 to 9, then we know quite a lot of things about their structure, even independently of knowing anything about what that structure represents, just thinking in terms of patterns of pixels. So we know that there are generally black pixels along the edges, and there are correlations. So if you have a lot of black pixels together, it's likely that they will border more black pixels. You wouldn't see the kind of speckled pattern that you get in noise. But at the same time, if you have a few white or gray pixels in a line, then up to a point, it is more likely that you will continue that line, whether it's straight or curving. So while these images can be represented as 28 by 28 numbers with values that vary between 0 and 1, the elements of that space that actually are digit images just fall in very specific regions of that space. So you can then think of the space as having an associated probability density that spans all of the 28 by 28 combinations of pixel values and has low points over the vast regions that are noise and peaks where we have data points. Okay, so now all we have to do is extend that intuition based on the MNIST digit in a few ways. So now we're thinking in full color. That just means that unlike grayscale, where you need one number to represent the intensity of a color at a pixel, now we'll need to know the intensities of red, green, and blue. And then we'll extend it, so rather than having 28 by 28 pixels, we can deal with arbitrarily large resolutions. And then finally, rather than just representing MNIST digits, we want to think about representing images in some kind of full generality. So we're going to need about 3 million numbers to represent images like this. And again, we will have a probability density associated with the images in this space. So we can say that the goal of generative modeling is to fit a model to that complex distribution in order for us to sample from it and thereby synthesize new data points, i.e. images. Okay, and if it's still not intuitive what this probability density looks like, you can take this advice from the grandfather of AI, Jeff Hinton. Think about the lower dimensional case, right, the 2 pixels, and then just tell yourself 3 million. So looking ahead, there's going to be some maths, and then after that, there's going to be some pretty pictures. So we're going to cover the 2 main parts of a latent diffusion model, denoising diffusion models, and then variational autoencoders. And then at the end, we'll look at tasks for latent diffusion models. Okay, So denoising diffusion models, this is how the generation happens. So let's say forward diffusion is the process of adding noise to an image. So we're going to iteratively add a tiny bit of white noise, step by step, to an image until the image is entirely randomized and it contains no information. And likewise, reverse diffusion is the inverse process of removing noise from a sample of initially pure noise to arrive at data that looks like it's been sampled from our original data distribution. And the gist of what we're trying to do is we're going to create a process that iteratively adds noise to an image and then train a model to be a noise remover. So we have this nice quote by one of the authors of a key paper on denoising diffusion models, which is creating noise from data is easy, creating data from noise is generative modeling. So we'll go on to see how we can remove noise by solving stochastic differential equations in such a way that we recover the original data distribution. Okay, so this is just to show you what diffusion looks like. We have an image over here on the left. Forward diffusion, we're just adding noise to that image until like here, it's completely corrupted. Reverse diffusion, the inverse process, we are taking noise away little by little from a sample of initially pure noise. Okay, so if you consider that forward process, we normally index this with a time variable t, ranging from 0 to, say, some big T. And these increments are called time steps, but that's really just because the index t imposes an order and a transitive dependence on successive steps in the process. X of t is the image at time step t. So as t is tending towards big T, this image is going to get noisier and noisier until eventually it's just pure white noise. And we'll let P sub t be the probability density at t. So this is like the noise distribution at time step t. So at big T, there is no more information remaining in X. And we can choose P of big T just to be a simple Gaussian. And of course, P sub 0 is entirely uncorrupted, and that's our original data distribution. Okay, so the forwards diffusion process can be modeled as the solution to a stochastic differential equation. But just to be sure that we're all on the same page with terminology, just really quick recap on ordinary differential equations. So an ordinary differential equation is just an equation involving derivatives over a value that's normally thought of as time. So, for example, dz dt is just a function in t. This is the form of an ordinary differential equation. Okay, so a stochastic differential equation is just a differential equation that has an extra function component for a further stochastic process. So here's the general form here. And we call this f component the drift, and g is the stochastic component. W is a finer process, which is also called Brownian motion. And SDEs are used in things like financial modeling, where you have a price which is evolving over time, or in physics for modeling the behavior of particles under random motion, like this ink diffusing in water. And you can represent forward diffusion with an SDE too. And it can be something really simple, like this. So here our equation is just sigma to the t. And then the solution will be a set of noise states a set of x of t for various discrete time steps throughout our time schedule. Okay, so the key insight that lets us do denoising diffusion models is that the reverse diffusion process, the backwards process that denoises, is also a diffusion process, and it can also be modeled as an SDE. So here is a general form. W bar is Brownian motion in the reverse time direction. And one way you can think about this is by understanding that the insights that led to this kind of generative modeling came from physics, from non-equilibrium thermodynamics. So if you think about the ink diffusing that we saw on the previous slide, the final state after all the diffusing has finished is that the ink particles are uniformly distributed through the water, and that's a state that we can easily model. And if you're able to just infer back one tiny step at a time from this end state, you can obtain the initial conditions. And that's something that was like a task in physics that was well understood and was the inspiration for this area of machine learning. Okay, so in this general form, we have this term here, which is called the score. And the score is the gradients of the log probability for the probability PT. So it turns out you can learn the score via a model parameterized with a neural network. And this process is called score estimation. And it's the fact that you can learn this term, the score, for each time step t, that allows you to construct the reverse SDE. And then there are numerical methods that you can use to solve it. Okay, so I won't go into detail about how score estimation works, besides just saying that it does. But I do want to give a high-level diagram just so you have an intuition about what exactly it is. So as the definition says, the score is the gradient of the log of the probability. And here's an example of what exactly that means. So suppose your probability density function was a mixture of two Gaussians, like this one here. Then you can think of that probability density function as the contours shown in this diagram over here on the right. So right, here's a region of high probability, and here's another region of high probability, right, like these two peaks here. And in between them, we have an area of relatively low probability. So in that case, then the score function, that should say the score function, can be seen as the vector field over this space, where the vector field is a vector tangent to each point. So the score kind of approximates a probability distribution. You see it's sort of wrapping this, this probability density. Okay, so now we can put all of this together. So we know that a stochastic differential equation that has this general form will have an associated reverse time SDE with this general form. And we chose our forwards SDE, our noising process, to be this relatively simple stochastic differential equation, sigma to the t. So then what we're going to do is just plug this into the general form and then see what that entails about the form that the reverse version takes. So if we look at this in the general form, then our f is just 0. We don't have a function here in x. and G, our stochastic component, is just sigma to the T. So if we plug in that F and that G into the reverse SDE, then we get this. And this chunk here is the score, which we know we can estimate using score estimation. And sigma was just the constant that we chose when we defined our forwards noising process. So we're then able to solve this reverse SDE, which just means that what we can do is we can denoise for one time step T. And we do this time step by time step, working backwards from big T to 0 until we're able to sample something that came from the original data distribution. So we're able to sample from our initial P of big T because we chose that to be something we could model, just a simple Gaussian. And then we can solve the reverse time SDE for that, enabling us to sample something from P of T minus 1. And so we proceed, obtaining incrementally less noisy samples until we end up with something that is entirely unnoisy and came from the original data distribution. Okay, so now you have an idea about denoising. What I wanted to show you here was a profile of the computation process of running this algorithm on a modern GPU. So the thing to notice about that denoising diffusion process as an engineer is that it's completely non-parallelizable because it has these long data dependencies. Each reverse diffusion time step depends on solving the one before it. So we just have this irreducible chunk of compute that has to be carried out in series. So here's what that looks like on a modern GPU. So here I did 50 steps of denoising, which correspond to these 50 blocks of compute. So the number of denoising steps correlates with the output image quality up to a point of diminishing returns. So we've seen that denoising diffusion models are an effective method of sampling from image distributions, but given this, execution structure, they're not exactly efficient. And we know that for generative AI, latency is really important. And the other thing to notice is that this denoising process is really compute intensive, and that intensity scales with the image size. So what we do is we add an extra trick that shrinks the number of parameters that the denoising algorithm has to work with. So that's it. So what this does is cuts down the compute footprint, and then that boosts latency. So the insight is, rather than doing your denoising in what we call pixel space, which is the 1024 by 1024 by 3 dimensional space, so height width channels dimensional space, we're going to do the denoising in a smaller space referred to as latent space. And that's what gives rise to this final step, which is a decoding step that pulls your latents back up into pixel space. So this encoding, decoding process means that you can do your denoising in a smaller space on these latents that has a much smaller compute footprint, and then decode the output of that in a way that doesn't lose any relevant information back up into your pixel space. Okay, so we do that decoding with the variational autoencoder. And here's a very high level diagram of what I mean. Right, image goes in, it gets encoded. We do the denoising here. This is denoising diffusion model. The outputs are decoded and they get returned to us as objects in pixel space. So latent here just means hidden, and it refers to the internal representation of the data features, like an intermediate variable. So latent space is really just a kind of intermediary representation of the same data that we have over here in pixel space. But like all good representations, it has some nice properties that make it more practical to work with than working with the data itself. So latent space representation of image data is efficient. And that means it makes do with fewer parameters. And it does this by abstracting away data that's either high frequency and within an image and therefore needn't be encoded over and over, or is imperceptible to humans, which just means that any changes to that part of the data wouldn't yield any corresponding difference in like the classification or the labeling of the image by humans. So the VAE is really what puts the latent into latent diffusion models. So for the next section, I'll give an overview of variational autoencoders, and then we'll see how they fit into the overall latent diffusion model. If you're already familiar with autoencoders, which have this encoder-decoder architecture, then you'll know that these are also a kind of generative model. So it might seem a bit funny that latent diffusion models are like a generative model wrapped in a generative model. But in this context, the VAE is doing this job of projecting into and then pulling out of the computationally more manageable space. Cool. Okay. So to set up the problem, we want to get a model of our complex data distribution, P of X, drawn over here. And the way we approach this is by taking a proxy distribution, P of Z, for a latent variable Z. And we're relying on this latent variable Z to tell us about P of X. So the approach taken by VAEs is to assume that you can choose the latent distribution. So we'll choose it to be a simple Gaussian with zero mean and unit variance. And the important thing to note here is the reason why this assumption is valid is that you can generally generate any distribution by taking a set of variables that are normally distributed and then passing them through a sufficiently complex function. So in a way, this is like what deep learning tells us, where there is structure in data, we can learn that structure with an appropriately complicated set of nonlinear equations. Okay, so for our proxy, P of Z, we can relate it back to our original data distribution via the law of total probability. So the law of total probability just tells us that the probability of X is the probability of X given Z times the probability of Z for all Z. So for discrete Z, you can just consider summing over all the possible Zs from Z1 to Zn. And then for a continuous random variable, you generalize by saying rather than summing over the Zs, instead you want to integrate over all of them. Okay, so suppose that you had access to this conditional probability distribution, probability of X given Z, then you could use this as a mapping that takes Zs to X's. We actually learned this conditional probability as a neural network that encodes the probability of X conditional on Z. So here, when I've written this, I've added this additional parameter theta just to indicate that this is a model that's learned as a neural network with parameterization theta that we will need to learn through an optimization process, which can be gradient descent. Okay, so our job then is to find a specific parameters theta that maximize the likelihood of each x in the training set under this generative process. So you can write down something like this for the objective. So here I've just indexed over the finitely many x's in our training data. And I've also assumed that we want to maximize the log likelihood rather than the straightforward probability. Because one thing that you kind of, I guess, like learn quite quickly if you do any probabilistic machine learning is that taking logarithms of probabilities has slightly nicer properties because you can distribute the log through a product. And also because if you're working with very small probability, so like values that are very close to 0, log is going to project that difference out. So computationally, you're not going to run into like limits of what your numerical precision can represent. Okay, so that's our task. And conceptually, it's not too complicated. You could say, well, I just keep sampling Zs. Sorry, this should say P here. There's a missing P of Z in this. You could say I'll just keep sampling Zs in order to approximate this. But the problem is that you would need to sample a lot of Zs, and most of them wouldn't correspond to any X's. So that's to say that for most Zs that you pull from your proxy distribution, probability of X given that Z will be 0. And so that Z will contribute nothing to your equation. So what we do is we also turn the problem around. For each X, there are some latent variables within our distribution over here that make that X more likely. And then we say, okay, let's just restrict consideration to those. So here is an X over here. And over in the latent distribution, we have some collection of Zs that correspond to that data point. And the fundamental idea of VAEs is that we will just sample values of Z that are likely to have produced X. And that means that you need another proxy, Q of Z given X, which is the posterior distribution of latents for a given data point. So think of this as the latents that would correspond to that data point. So if we had this, then we could compute, for instance, the expected value of the probability of X given Z, just restricted to those Z sampled from Q. So this would allow us to find the most likely X given Z. In practice, actually constructing this posterior is non-trivial, and this is the goal of variational inference. But because time is limited, I'm just going to note that this is a hard problem, albeit one that is solvable, and then we'll move on. Okay, so what we have here is a summary that will just tie those intuitions together. So we have a probability distribution that we are trying to shortcut, the probability of X given Z. And then we have this convenient distribution that we're considering Q, that is the distribution of Zs most likely to have produced an X. And then we'll just state a couple more definitions. So we have a definition of this two-place relation between distributions Q and P of Z given X. So this is Kullback-Leibler divergence. And again, because this is a high-level overview, for now, just think of this as a two-place relationship between distributions that can be used as a measure of how similar those distributions are. Our second definition is Bayes' theorem. So, a very core principle of probability theory. And the reason why I'm showing you these is because you can use Bayes' theorem to rearrange this statement of KL divergence into a form that's going to be helpful. So what I have here is just a little bit of algebraic manipulation of Bayes' theorem, starting by taking logs of each side and then distributing the logs through. And the reason why this is helpful is because you can then use this new form to substitute into our definition of KL divergence. So we'll replace this final term over here in the expectation with its equivalent form according to this expanded version of Bayes' theorem. And once we've substituted into that definition, we obtain this final line here. Okay, so this form here is valuable because if you look at what it's saying, we've isolated on the left-hand side that probability distribution that we wanted to model P of x, or at least log of P of x, minus this KL divergence term, which you can consider to be an error term. And given appropriate choice of Q, we can get to become very small. And over here on the right-hand side, we have something that can be optimized via stochastic gradient descent. So this P of x given z is our neural network. And then we also have another KL divergence term here. So obviously this is like a big topic that rewards detailed study. But even at this high level, you can see that you can interpret this as telling us that we've bounded log P below by a likelihood term, and that by varying choice of Q, we're able to bring that bound quite close to P. And so this should give you an intuition of how it's possible to train a VAE. And once you've trained, once you have a pre-trained VAE that does the job you need, you can then combine it with lots of different denoising diffusion models. Okay, so we're now able to put the components together. So do you remember the score generating model? This thing typically has the form of a U-net. And U-nets are a very common architecture for computer vision. They're used, for example, for tasks like segmentation. And they use convolutions to first downsample an image. So this downward side of the U is passing the image successively through conv layers that force it to smaller and smaller parameter sizes. And then the model upsamples that same image over here on the right-hand side. And then we also have these residual connections between layers. Okay, so given that, we can now look at the end-to-end architecture of a latent diffusion model. Okay, so I included this diagram because it's the frequently reproduced diagram from the original latent diffusion paper. And it can be quite hard to understand, I think, without all of that preceding context. So this image is a little bit more complicated than it needs to be because it shows you the structure of the model as you'd use it in training as well as inference. But we only care about inference. So we just want to see what a forward pass looks like. So we don't need to consider backpropagation. And at inference time, we're not going to be doing any noising, which is this forwards diffusion process. We just want to remove noise, denoising, which is what actually does the generation. So that happens here in the denoising U-net. And At inference time, this step will get replayed 50 or so times. We pick a sample of pure noise over here, write our latent at big T, and then time step by time step remove that noise. So over here at the periphery of the model, we have this encoder E and decoder D that get you out of and then back into pixel space. At inference, we just need to decode. We just need to get out of latent space. And we'll do this with our pre-trained VAE decoder. Okay. So I wanted to say something about how we accelerate computation on latent diffusion models like this to reduce latency. But it's really like mostly very high-level global techniques that are useful. So you want to be sure that you're using the right 16-bit or smaller numerical formats. And then likewise, there's a lot of benefit to be had from using a compiler that supports operator fusing, right? So you never want to be like running PyTorch mode in production. And then because virtually all of your flops are spent going round and around this unit, any optimization you can make to its tensor ops will have a really large payoff just from that cumulative effect of running it over and over. Okay. And then something that we haven't really touched on at all is the semantic conditioning, because practically you don't just want to generate samples unconditionally from P of X. That would just give you anything that could plausibly have been sampled from our data set. So for what's called text to image generation, you use cross attention to inject semantic data from a text prompt at runtime into the downsample blocks of the unit. So that denoising process is guided by semantic information. So for the remainder of the talk, I want to show how flexible and how powerful that conditioning can be. So you'll also hear semantic conditioning described as guidance. We're guiding the image generation with text or with other data, such as image data. And via text guidance, these models can produce images that don't match any specific image in the data set, right? So there's no images of somebody riding a unicorn in the moon on the training set, but the model knew how to make one. Okay, so I promised there would be pretty pictures. So here are some peonies from our latest Stable Diffusion 3. And here are some images of eucalyptus leaves under strong sunlight. So you can see that there's like an overall coherence to the image in that the model is aware of how the light is hitting the surfaces and where the shadows fall. Okay, so we've seen that text embeddings can be used to steer the path taken by the denoising, but text isn't really the best interface for manipulating images. And there's a huge amount of capacity that these models have learned that's really impossible to control just via text prompts, simply because text is too blunt an instrument. So we've also developed the ability to use data, including image data, to control image generation. So one technique you can use is just to initialize the first noise state with some image data and then transform from there. And this is called image-to-image inference. But actually, I think a better way of using image data to guide latent diffusion models came out in these techniques called control nets and adapters. So the idea behind this is that as well as injecting in text into that unit down block, you can inject other kinds of tensor data as well. So Adapters, for example, put an additional model before the latent diffusion model, this adapter, which will capture some information from something that's supplied as an image, and then it will pass that information to the latent diffusion model. Okay, so suppose we have a depth adapter, then this will allow you to pass in a depth map as well as a prompt. And then by varying the prompt, you will get out different images, but they adhere both to the prompt and to the depth map. So you're basically using that depth map to restrict or control the generation space. So for example, this kind of thing is a depth map, and we'll pass this into our adapter. And then over here you have an output picture, this person, which matches the depth map. So the relative positioning of the features in 3D space is the same, but the surface level details are different. Here's another nice application of this. You can basically paint on a new kind of surface level details of a room. We also have sketch maps. They guide generation on the basis of a sketch. So here the sketch is doing a similar job as the depth map in restricting the space of outputs. You can match the edges of a line drawing. It's a very similar idea. So here we have a line drawing of a van. We can generate it, shrink it, change the color, apply some kind of horror film tropes, make it sci-fi. You get the idea. Other restrictions you can impose on image gen include the requirement that the edges of the output image allow for tiling. So this means you can concatenate the images together and get a seamless overall image. You can use the model's representational capacity to upscale images using a more sort of generative method than traditional interpolation. Something else that's helpful is the ability to modify images in a really targeted way, and this is called in-painting. So along with your initial image, you supply a mask to the model, and it will restrict generation just to the masked area, again adhering to the prompt. So for a lot of commercial use cases, you really just want to update some images, and in-painting can be much more simple to use than something like Photoshop, because the underlying model is already aware of things like how shadows fall and how textures are visually rendered. So it's easier to let these abilities just emerge from the model than it is to apply them manually. Okay, for a long time, these models really, it was kind of well known that these models really struggled with hands. So hands are very complicated. There's a lot of different ways that hands can be in the training set. And as humans, even though hands come in all different shapes and sizes, we're very sensitive to things that look a bit off, right? Like the fingers being weird lengths relative to each other. So it makes it very hard for models to generate convincing hands. Happily, that problem has mostly gone away at scale as the model sizes have grown. The next challenge was generating text. So just like hands were often a bit of a giveaway that something was AI generated, garbled text is also a bit of a giveaway. And obviously we're very sensitive to text that is even a little bit wrong. But the ability to generate coherent text isn't the kind of thing that's just going to go away by training more. So we've now solved that problem for short strings of text. And it's generally good enough to render like short combinations, even unusual combinations of words and things like signs and so on. So that ability to render text in image gen models was achieved by a modification to the latent diffusion architecture. The new architecture, called diffusion transformers, was introduced by Peebles and Shear William Peebles is now leading Sora development at OpenAI, and a very similar architecture called multimodal transformers were used for Stable Diffusion 3, the latest stability AI model. And essentially what you do is replace that UNet backbone with a transformer-based model. So this enables better representation of text in images. And we can operate on sequences of images. So transformers are they're very good at learning and representing those long-running data dependencies in sequences of language or code. They're the reason why LLMs work. In this vision setting, diffusion transformers can learn from and can sample sequences of images, right, which is to say video. So I'll wrap up now, just with a nod to the near-term future, which is multimodal Gen AI. So multimodality means a model that can ingest and output data in the form of text, audio, video, and form a single coherent representation that all these media contribute to. And this is the promise of these so-called AI assistants or agents. If you think about being able to use it like your phone camera to capture video stream input and have a model interpret it, and then interact with that. So, the implications of this for robotics are pretty significant. And I also personally think that we're going to see some huge payoffs from reinforcement learning once we can deliver on multimodal modeling. So with that, I will wrap up. Thank you so much for the opportunity. Happy to take any questions.
Thank you, Kate. That was a really nice talk. And I think it was a really nice overview for people that not used to, or they're just not familiar with diffusion models. I think it was really nice, especially for myself as well. If you have any questions for Kate, you can type them in the chat, or you can raise your hand and unmute yourselves. Yeah, Yiming has a question. Do you want to go ahead?
Hi, Kate. Thank you very much for the talk. It's very insightful. I have a question maybe more related to, practical practices. So when you train a large model like this, like the stable diffusion, how do you decide how much data is enough data? And do you have a way to validate like the contributions of each data samples? When do you know when to stop collecting new data?
That's a really good question. I don't work on training, so I'm not an expert on that. I know. I think if you read the publications from our research team, they have details about how the training data was collected and how much data we have. And I would guess, but I wouldn't be sure, that our research team maybe have used techniques to look at like how much different kinds of training data is contributing to the weight updates. In terms of how do you know how much data is enough? I don't know. I feel like the more data, the better, maybe, but I don't. I'm probably not the person to answer questions about training, I'm afraid. But I would say take a look at the papers by Stability's research team, and we're big believers in open source and publishing our methods. So there'll be data in there.
Thank you very much.
Thank you, Yiming. There's a question from Jan. He says, what is your perspective on applying these models to other types of data apart from images, like chemical structures, for example?
Interesting. I mean, I would personally love to see these techniques, which are extremely powerful, be used to synthesize data that then has applications in science. And I know I remember seeing a publication on using diffusion models in material science. So I think it's an active area of research. Yeah, I think it's like I think it's a really interesting area. I would love to see it come to fruition. I think, a lot of the research is driven by these because generative AI is so new, people like these cool applications like making videos or making images where you can see, visually it's impressive. And I think these techniques are going to trickle down into more scientific applications that will have big benefits for science.
Thank you, Kate. Yeah, Jan says thank you. And we have a question from Andrea. He says, hi, great talk. Could you please point us to the stability AI papers or projects that use control nets and or adapters for image conditioning?
Yes, sure. I will find a way of sharing the papers. They're all on archive. And then there's so adapters came out of Tencent. And now they're used quite widely, and then control nets came shortly after, but all of this came out in the last 12 to 18 months. And then there's loads of small apps and startups applying these, but it's I personally think they're really cool, and we haven't even seen a fraction of their potential yet.
Yeah, cool. Yeah, Andrea says thank you. Stephanos, he is asking how big the value of t usually is, and is there any intuition behind the number of time steps used? Does always longer t make better results, or there's a threshold that after it passes, then it becomes worse? And thank you, great presentation.
Yeah, so for different models, there will be a recommended value of t. So 50 is the recommended hyperparameter for our latest Stable Diffusion 3. And it depends on the noising schedule when the model was trained. So when you train it, you do some forward diffusion. And this follows a schedule. So there are different kind of schedules that you might take. And so depending on how you trained it, that will determine the optimal value of t at inference time. And typically, if you just do a very tiny number of time steps, you get an image out that is still very noisy. And then there comes a point, say, if you carried on going, you could carry on going for 150 steps, but the image wouldn't be 3 times better than it would. After a while, it would just sort of start, tweaking little details and not exactly improving the image quality. So you kind of top out the benefits around that point that's entailed by the way it was trained, and then it's diminishing returns.
Yep. Thank you, Kate. Is that okay, Stephanos? Yep, he's happy with that. And then Mike, he says, hi, great talk. I was wondering if you had any experience with distilling the denoising model to speed up the generation.
Personally, no, which isn't to say that it's not something that people have tried. I know, so we create turbo models, which are kind of fast, lightweight versions, which I think they are adversarially. I think they use some kind of distillation to create them, and those models, the reason why they're so fast is because you just need a very small number of time steps. So yeah, I would say, I don't know, I would have to check the research. But I think it's models like SDXL or SDXL Turbo, I think use something like that.
Thank you, Kate. Before going to Phil, can I ask a quick question? What are your thoughts on consistent character generation? For example, in the slide when you're showing the scarf going from brown to red, it's not the same scarf.
Mm-hmm.
So like, what are your thoughts? Or is it something like, yeah, what's your view on that?
Yeah. So it's not the same scarf because we masked that area, the model can't use that data. So it's just going to make a new scarf. There are ways of sort of isolating some object within the model's representational capacity. So you can do a kind of inversion technique where you find some area of image space that you care about, so some very specific object, and then you basically give it a name. You kind of fine tune a little bit the model so it knows this specific thing, and then you can continue to generate that object. And I think that's been superseded now with like low-res, so low-rank adaptation, which is a more like recent version of like a more kind of widely used version of fine-tuning now. And then there are startups that are really focusing on this because it unlocks, you can like tell a story and so on. So it's definitely something that people care about, and I think it's enabled with fine-tuning techniques.
Okay, yeah, thank you. And I think we're gonna take the last question from Phil. Phil, you wanna go ahead?
Yes, thank you. Kate, I enjoyed your talk.
Thanks.
If someone was to, there must be some area you'd like to see worked on that you're doing other things. Is there something that I could, or maybe someone else in the audience could pick up and carry forward?
I mean, I do feel like this is such a powerful method that I would love to see it applied in areas that require real domain expertise, like, synthesizing new chemicals or materials. I would love to see like a kind of proliferation of applications outside just image gen. So I would say, yeah, for people that have that like multidisciplinary, subject matter knowledge in one area, as well as being able to apply the machine learning, I would like to see, that.
Okay, thank you.
Thank you, Phil. If you have time, Kate, can we take one more question from Ignacio from the chat?
Yeah.
Yep. He said, thank you for the talk. Do you believe it will be possible to synthesize physical properties directly out of the image generation process, like lighting, direction, or texture properties, without additional training data? Like, for example, the control nets, given the global consistency of the images generated? That was a question I was going to ask as well. So,
okay. Yeah, so this was like an interesting discussion people were having around the time that Sora came out, which is a very similar architecture to Stable Diffusion 3. I think there was like a blog post or something by OpenAI that said you can think of this as a world generator because this model has, it's been exposed to so much training data that show it how, like, water swirls or whatever. You don't need to teach the model the the laws that generate, what is it, like the Navier-Stokes equations or whatever. You don't need to teach it the laws that govern these processes, because it will just learn that from having seen, it will learn the behavior of water because it has just seen so much water swirling and flowing and so on. So yeah, I mean, there's a potential for the model to learn how different textures and things appear. So if all you care about is getting an image of that, then all you care about is that it appears correct. If you want more than just a visual representation of the thing, then these, you're going to need to change the data. You can't just train it on images. You have to train it on something else. But yeah, like these things can certainly synthesize textures and things they've seen. I'm not sure that answers your question. Did that answer your question?
Yep, he says yeah.
Okay.
Thank you, Ignacio. Yeah, I think I've read somewhere that they probably use like Unreal Engine for training their models. Well, I think we can leave it up to here. It's past 5 now, and yeah, thank you so much, Kate, and thank you everyone. That was a really insightful talk. I really appreciate your time, and for everyone, yeah, this is the last one of the academic year, so probably see you back in September. Thank you, Kate.
Thanks so much. Bye-bye.
Bye-bye.